So good afternoon, students. So we will begin with our today's session. In yesterday's lecture, we saw how to write a program to transmit data serially on TXD pin of microcontroller. Today we will look into how to receive data serially on RxD pin of microcontroller, and then we will go for interrupts. Okay. Let us look into the problem statement. Write a program to receive 5 characters serially on RxD pin of 8051 microcontroller with 9600 baud rate. Okay, so now we are going to write a program for serial reception. Yesterday we saw serial transmission. Okay, so today's program is reception and receiving how many? 5 characters. I didn't mention which are the characters, but we know we will be receiving 5 characters serially on RxD pin. And the baud rate is given 9600. Oscillator frequency given 11.0592 megahertz. Take the frequency whatever is given to you. If the oscillator frequency is not given, students, always take this frequency 11.0592 megahertz. So for serial reception and serial transmission, right? So as to start writing the program, the first thing that you should do is the baud rate calculations. So the first step, for 9600 baud rate and 11.0592 megahertz oscillator, what is the count that is to be loaded in TH1 register? So the thing is, do the baud rate calculations. Second thing is, write the control word for TMOD, timer 1, mode 2. So the second step is, find out the control word to be loaded in TMOD register, right? Timer 1 in mode 2. Then write the control word for serial communication, SCON control word. Now what is that SCON control word? We are going to receive 5 characters, and every character is an 8-bit ASCII code. Correct? So it means the serial reception is of how many data bits? 8 data bits. And the baud rate is decided by the user. So that comes under the category variable baud rate. Correct? So the control word for SCON is 8-bit asynchronous communication and variable baud rate. 8-bit UART and a variable baud rate. So that is the control word we will initialize in SCON register. And after these 3 initializations, the count, TMOD, SCON, we will start the timer. Is that okay? Now, as soon as we start the timer, we will keep on checking the RI flag, receiver interrupt flag. If RI flag is 0, mean the reception is still going on. Wait and continuously keep on checking RI. So this thing will be done by the instruction JNB, jump if the bit is not set. Which bit? RI. And if that bit is 0, keep on waiting and checking. Correct? So that is the instruction we will use to check RI flag. RI flag is 0, wait at the jump instruction. And if RI flag is 1, mean the reception is completed. Clear the RI flag. So RI flag is 1 indicates the reception is completed. Microcontroller has received the character. Now where has the character received? The character received is in SBUF register. Okay, so when the reception is completed, we should read the SBUF register. So reading SBUF register, and we will store the character in accumulator. So we will do this with the help of instruction MOV A, SBUF. Okay, now see here students, whenever that reception begins, mean the bits are received by microcontroller on the RxD pin, 1 bit by 1 bit will be received. Right? So whenever 1 bit is received, internally it is not that it directly gets loaded in SBUF register. Okay, right? The loading, when the reception happens, immediately it is not kept in SBUF register. When the bit is received, it is first kept in a temporary shift register. there is one 8-bit shift register internally. The user does not have access to it. It is used by microcontroller to storing as soon as that one bit arrives, one bit by one bit arrives. Okay, so whatever bit arrives on RxD pin, that initially gets saved in that internal shift register. Second bit arrives, it is saved in that shift register. Third bit, fourth bit, and finally when all the 8 bits arrive in that shift register, right, internal shift register, then microcontroller picks up those 8 bits from the shift register and then loads it in SBUF. Are you getting me, students? So one by one, as the bits are arrived, they are not directly kept in SBUF. They are kept in an internal temporary shift register. And when the shift register receives all the 8 bits, microcontroller picks up the data from the shift register and loads it in SBUF. And user can only access SBUF. Okay, so when all the 8 bits are received, that indication will arrive on RI flag. RI flag will be set. We will clear the RI flag and then pick the character from SBUF. Hope you are getting me, students. Now see, how many characters are we going to receive? We are going to receive 5 characters. So when the first time RI flag is set, it means we have received the first character. Get the first character from SBUF, store it in accumulator, and from accumulator we will save it in memory. Why? Because I have multiple characters that I will be receiving. Microcontroller will be receiving multiple characters. So the first character whenever we receive, we will store it in memory. Second character when we receive, we will store it in the next memory location. If I do not do that, then the earlier character will be overwritten and it will be lost. Okay, so since my program statement is telling receive 5 characters, right? I will pick the character from SBUF, save it in accumulator, and from accumulator I will save it in memory. This is the modification because of the problem statement. Okay, and then I will repeat steps 5 to 7. That is, keep on checking RI. If RI is 1, clear that RI flag and pick the second character from SBUF. Again, repeat to step 5. Keep on checking RI. If RI is set, clear the RI flag and copy the third character from SBUF. And I will repeat this steps 5 to 7. How many times? 5 times to receive 5 characters. Okay, students. So with this algorithm, let us start writing the program. Program for serial reception. Okay. First baud rate calculation. Okay. And then tmod scon, and then we will write the program. So let us see the baud rate calculations. What is the baud rate given? 9600. See here, students, in exam, the baud rates can be different. It can be 2400, 4800, 9600, 19200. So be careful with what baud rate has been asked. Accordingly, do the calculations. In our lectures, I have taken 9600 baud rate, right? And then the SMOD bit, generally it's not mentioned. Always assume it with 0. You can assume anything, but follow that in the calculation. So we are the problem statement is mentioning 9600 baud rate, and we have assumed, I have assumed SMOD is 0. So with this, we go for the calculations. So baud rate 9600, 2 raised to SMOD, SMOD is 0, so 2 raised to 0 into 11.0592 megahertz, 10 raised to 6 upon 32 into 12 into 256 minus TH1. What are we doing? We are finding the count that is to be loaded in TH1. So what does TH1 come? 253. That is FD hex, converting it into hexadecimal. So FD is the count that is to be loaded in TH1 register. Timer 1, mode 2. Okay, so this count will generate one square wave. And with respect to that square wave, mean that will give you a baud rate. So with respect to that square wave, 9600 baud rate, the bits will be received by microcontroller. Okay, students. So that is the baud rate calculation. Then we will see the control word for serial reception, SCON. So look into the red colored letters, right? This is that SCON register, that blue color register. What are we doing? 8-bit reception, UART, and variable baud rate. So that is mode 1. So SM0, SM1, that is mode 1. It is a single processor communication. So SM2 bit is 0. We are going to do the reception. So enable the reception. REN bit should be set. We are doing 8-bit communication. So the TB8 and RB8 are the 9 bits. What are we doing? We are doing only 8-bit communication. So these 2 bits will be ignored. Don't care. So don't care. Generally, I keep it as 0. And TI and RI are the flags. These are set and cleared by the serial communication hardware. Okay, so these bits, so we have kept it 0, 0. So the controlled word for reception is 0101, that is 5, and 000, so that's 0. So the SCON control word is 50 hex for reception. Yesterday we saw transmission, so the SCON control word came as 40 hex. Now we are doing reception, so the control word is 50 hex. Okay, and then one more control word that we need is TMOD, timer 1, mode 2. So yesterday we saw TMOD, the control word came as 20 hex. Okay, so we did the count calculations. We find out SCON control word 50, TMOD control word 20. Okay, so we found out the count FD hex. Then the TMOD was 20 hex control word. SCON, the control word is 50 hex. Then we start the timer by setting the run bit. TR1 is set. Then we keep on checking the RI flag with the help of instruction JNB RI. Jump if the bit is not set. As soon as the bit is set, microcontroller will come out of the jump loop. We will clear the RI flag and we will copy the character from SBUF in accumulator. The character received is in SBUF. We take the character from SBUF, save it in accumulator, and we will be saving it in memory. And we will repeat this reception process 5 times. So step 5 to 7 will be repeated 5 times. Okay, so we start with our program. Now see your students, I said problem statement is telling 5 characters. So let us take one memory location, and as soon as the character is received, let us save in that memory location. And let me assume internal RAM address 30 hex. This is our assumption. Problem statement does not say anything. So let us receive the character, save it in memory. Which memory? Internal RAM and address 30 hex. So this is our assumption. So let us do that first as an initialization. So ORG00, sjump next, and from the next label we start. And what is the first instruction? That 30 hex address, let us save in R0 register. Correct? And let us use R0 register as a pointer at the rate R0. For what purpose? Storing the received characters. So the first thing is MOV R0, #30 hex. At this memory location, we will be saving the character. And how can I access the memory location? With the help of R0 pointer. Okay, so R0 is initialized with the address. Now such 5 characters are to be received. So I need to loop the reception 5 times. So I need one counter. So I copy the number 5 in register R2. MOV R2, #5. Why? Because the reception should be repeated 5 times. Microcontroller will be receiving 5 characters. Right? Now, load the count FD hex in timer 1 TH1 register. Load the count TMOD control word 20 hex is loaded in TMOD register. MOV TMOD, #20 hex. And we start the timer. So set the run bit TR1. So timer has started mean the square wave generation has started. That baud rate 9600 baud rate square wave has started. And now we enable the reception. So load the SCON control word. 50 hex is loaded in SCON. It means the reception is enabled. And immediately the bits start arriving on RxD pin. Okay, so loading that SCON control word, the reception gets enabled. So the receiving has started on RxD pin. What we should do is keep on checking whether the reception is completed or not. That is check RI flag. How do we do the checking? Jump if RI bit is not set. RI bit is 0, jump. And where do you jump? At the same instruction and repeatedly keep on checking. RI 0, wait. RI 0, wait. And as soon as RI is 1, we will clear the RI flag. Where is the character available? In SBUF. So from SBUF, take the character in accumulator. So we have received the first character. So take that first character from SBUF, save it in accumulator. And from accumulator, we will save it in that 30 hex memory. This is what we have decided. Yes or no? That first SBUF character, we will copy and save it in accumulator. And from accumulator, I will save it in 30 hex memory location. How do I store it? R0 is pointing to that memory location. So the accumulator character, save it in the memory pointed by R0. So MOV @R0, A. So the first character received saved in accumulator is saved in the memory location pointed by R0. Okay. So we have received first character. Let us decrement the counter. DJNZ R2. One character received. Is R2 0? No. So go back for reception. That is repeat steps 5 to 7. Right? So repeating the step is checking RI. If RI is 1, clearing it. Second character is available in SBUF. Take it in R0, take it in accumulator and save it in the memory pointed by R0. Correct. Now R0 should point to the next memory location 31. At 30 hex, we have stored the first character. The second character should be stored in 31. It means R0 should be pointing to 31. Now what is happening? R0 is still pointing to 30. So before decrementing counter, I should have taken the pointer to the next location. So before doing DJ and Z, I should have incremented the pointer. Increment R0. So R0 will now show 31. Mean it will point to this next memory location. Okay. So before decrementing the counter, increment pointer, then decrement R2, the counter, go back, check RI. If RI is 1, clear RI. Take the second character from SBUF in accumulator and save it in the memory pointed by R0. Now R0 is pointing to 31 hex. So second character is loaded at the next memory location. And repeat this process 5 times. Okay. So 30, 31, 32, 33. At these memory locations, consecutively, I will have the 5 characters saved. And now this is over. Stop the program. At the end of your program. Correct. So that's simple it is. Serial reception. Okay, students. Right. So just a quick look at the program. We took one pointer so that to save the received characters. So the characters will be saved at 30 hex. 5 characters are to be received. So we loaded count 5 in R2 register. And then we did all the initializations required for serial reception. FD hex is loaded in TH1 to get 9600 baud rate. 20 hex is loaded in TMOD to use timer 1 in mode 2 auto reload. Then we started the timer. Then we started the serial communication by loading 50 hex in SCON. So serial reception begins. We kept on checking whether the reception is completed or not. As soon as the reception is completed, RI flag is set. Immediately we cleared the RI flag. The character is received is in SBUF. we took it in accumulator. From accumulator, we saved it in memory. We pointed to the next memory location and then decremented the counter. Correct. Now always remember, students, clearing the flags is very important. Let it be timer, let it be serial communication. If I do not clear that RI, correct? If I do not clear the RI and I go back, jump if the bit is not set. If I go back to checking RI, what microcontroller finds? RI is set. So that's an understanding. Second character has received. And it comes out of the loop immediately. So that reception will not happen properly if you do not clear the flags. So let it be a timer flag, or let it be serial transmission flag or serial reception flag. Whenever we check the flag condition, make sure that you clear the flag and then proceed ahead. Right? So clearing RI is very important. Okay, students. So I have already copied this program in Keel. So let me show the execution. So let us go to Keel program, which I have already done it. I'll only execute and show. Okay. Okay, I'll share the Keel window. Just a minute. I will execute and show that reception program. Hope Keel is visible. Just a minute. I think so. The Keel is visible. Okay. So let me open that program, which I had already done. Serial reception. Just a minute. Yes, serial RX reception. So see, students, whatever program that I was showing on that PPT, the same program is mentioned here. MOV R0, 30 hex, MOV R2, 5 hex, FD loaded in TH1, 20 hex loaded in TMOD, started the timer, SCON register 50 hex, check that RI, clear RI, from SBUF take it in accumulator, from accumulator save it in memory, increment that pointer, decrement the counter and repeat the reception, and then we stop. Okay, so let me check for any syntax errors. Build target. So 0 error, 0 warning, hex file created. Let us go for running the program, simulating. So debug, start the debug session. Okay, so see, I have already chosen that serial window, serial peripheral window. And now for serial communication, I told you we have, as we have memory windows, we have UART windows. So from this view, I have selected serial window UART1. Okay, and see, I have that UART1 window. Hope right hand side at the down corner. Hope you all see here. I am pointing the mouse. This is that UART1 serial transmission and reception window. Whatever is arriving on TXD pin, whatever is arriving on RXD pin appears here. The Keel software has given that provision. So this is the UART window. And besides that, this is the memory window. Okay, now what are we doing? Whatever the characters are arriving on RXD, we are saving it in internal RAM memory 30 hex. So see, I have taken a memory window and I have chosen I:30 hex. So these are the, I see I have highlighted in blue. So initially that 30 hex memory is all 0000. Okay. After running the program, what are we doing? Serial reception. Whatever characters we receive, we will be storing it at 30 hex, 31 hex, 32 hex, 33 hex, and such 5 characters. Now we have not executed the program, so the memory window is showing 0000 at those locations. Okay. Now what I will do is, I will run the program, burst execution, and whatever I type in this UART window, that will be going on that RXD pin. Microcontroller will receive that characters on RXD and automatically will save it in the memory. Okay, so let me run the program. students? So that is that run shortcut. I run the programs and see I'm typing here characters 6, 7, 8, 9, 4, 0. Okay. And one more character I'll type 2. So 6, 7, 8, 9, 0, 2. I stop the program and I look in the memory window. Right? And see here students, initially it was showing 30, 31 hex, it was showing 0, 0, 0. Now I'm able to see the characters. At 30 hex location, the character received is 36. The next location 37. The next location 38. Next location 39. What are these? These are the ASCII codes of the digits that I have pressed on the keyboard. What did I press on the keyboard? 6, 7, 8, 9, 4, 0. So digit 6, the ASCII code is 36. Digit 7, ASCII code is 37. Digit 8, ASCII code is 38. So whatever characters I had pressed on the keyboard, its corresponding ASCII code got loaded, was received on RxD and was loaded in those memory locations. Hope you are getting me. Now instead of typing the digits, let me type some characters. Let me type FAMT. Okay. So I come out of the debug session. I stop the debug. Okay. I again enter into that debug session. Okay. Now in UART window, I have selected the UART window. I will run the program. So that the shortcut run. The program is running. Now in the UART window, I am typing the characters F, A, M, T, right? And I stop the program and I look into the memory window. See here, can you see F, the letter F, ASCII code is 46. See, I'm highlighting in blue. A, character A, the ASCII code is 41. Character M, the ASCII code is 4D. Character T, FAMTT, the character is 54. Right? So I typed the characters in that UART window. They were received on the RxD pin. They were stored in SBUF, and from SBUF we saved it in internal RAM memory 30 hex onwards. So if I make this as an ASCII, you see, let me modify that ASCII. See, can you see? I have changed the memory window into ASCII format, and at 30 hex location, I have the character F. Hope you all are able to see the students. At 31 location, there is character A. At 32 location, there is character M. At 33 memory location, the character is T. So I have changed the memory window to show ASCII characters. And I can see that FAMT in the memory. Correct? Mean our reception program is working. Okay, students. Now, I have shared another screen. Now see here, students, that serial reception, right? Whenever we think of interfacing any device to microcontroller serially, this is how that interfacing diagram will be. Okay. Now you have 8051 microcontroller, and with the help of that serial pins TXD, RxD, you will be communicating it with the peripheral device. So at the rightmost corner, I have shown that peripheral device. Either it will be only receiving or it will be only transmitting. Okay. Now in between that microcontroller and that peripheral device, you can see those two ICs named as MAX 232 chip. Right. Now, whenever we interface these devices, right, serially, in between, we need to connect these two devices, and these are 232, MAX 232. MAX is maximum, right? There are many other companies also. So these are those two ICs, 232 ICs. Hope you all have heard about RS-232 protocol, students, right? That RS-232 protocol, it's a standardization done. How should that serial communication happen? So they have set protocol standards. They have set hardware standards that should be used during serial communication. So this MAX232 chip is a level translator chip, right? So there is one level translator chip at the microcontroller side, and there is another level translator chip at the peripheral side. Okay, now what are these two ICs doing? The name itself is level translator. It means it is going to change the voltage levels. Logic 0, logic 1 levels are going to be changed. Okay. Now this microcontroller, it is a digital device, right? At what voltage it operates on? 5 volt and 0 volt. Correct. So logic 1 is 5 volt. Logic 0 is 0 volt. The same thing is at the peripheral device also. That peripheral device will also be digital. Correct. So logic 1, it will be representing 5 volt. Logic 0 will be represented by 0 volt. But during transmission, right, you will be sending those 8 data bits. Logic 0, logic 1, 8 data bits. So for transmission is not done with those voltage levels. 0 volt and 5 volt, these voltage levels are not used during transmission. Why? Because it has very less noise margin. Now what is this? Noise mean it's an unwanted signal. What is margin? Ability of the circuit to work correctly even in the presence of noise is called noise margin. Are you getting me? Mean if microcontroller is transmitting 5 volt, some noise, unwanted signal will change that 5 volt. Even if there is a change in 5 volt, logic 1 should still be treated as logic 1 by the hardware. And that capability is called noise margin. Correct? Ability of a circuit to bear that noise. Okay. With 0 volt, 5 volt logic levels, the noise margins are very, very small. Is that okay? Mean then the signals will be sensitive to noise, and we do not want that. Logic 1 transmitted should remain logic 1 at the receiver side. It should not change to logic 0. Mean the transmission should happen correctly. The reception and the transmission should happen correctly. So then what is done? The noise margins are increased. Mean the circuit, whatever voltage levels are sent, right? Instead of 0 volt, 5 volt, the voltage levels are changed to plus minus 15 volts, plus minus 12 volt. Is that okay? So 5 volt and 0 volt will be changed to minus 15 and plus 15. So we are changing the voltage levels, and this voltage level change is done by MAX232 chips. Level translator ICs. Are you getting me? And for what purpose? So as to increase the noise margin. Larger the noise margin mean logic 1 will still remain logic 1 even in the presence of noise. Logic 0 will still remain logic 0 even in the presence of noise. Is that okay? So always while transmitting data, we need these level transmitters in between. And the conversion is done both the ways. What does this level translator do? 0 volt and 5 volt from microcontroller, it converts it into plus minus 15, plus minus 12, plus minus 10, and then transmits it. And at the receiver side, another level translator will convert plus minus 15 back into 5 volt and 0 volt, or plus minus 12 will be converted back into 0 volt, 5 volt. So it does both way conversions. 0 volt, 5 volt converts it into plus minus 15, and plus minus 15 converts back into 0 and 5 volt. And that's hence the name given is level translator. We never directly connect TXD and RXD of microcontroller to the TXD and RXD of the receiving peripheral device. Is that okay? We always use the level translators in between. So that's the interfacing diagram right? Serial reception and serial transmission. Hope you all get me, students, right? Now see, in on your PCs, there is one DB9 connector, right? Have you all seen that? Anyone? If you all have those old PCs, there is one 9-pin connector, and we call it as DB9 connector. And that DB9 connector follows RS232 protocol. Correct? So internally in that PC, after that DB9 connector, we have that MAX232 chip. Is that okay? So that's the interfacing of serial transmission and reception. Okay, students. Now in this diagram, I have not shown the other connections of MAX232 chip. This much is fine with, just to get an idea. There is a level translator in between, one at the transmitter side, one at the receiver side. Okay, students. So here we complete serial communication. So thank you for attending, students. Okay, I stop here. Bye and see you in the next session. Okay.